Okay, this week we'll introduce classification. We mentioned the supervised learning last week, right? So when the target variable is a numerical feature, is numeric variable, we use a regression. And when we have the target variable as a categorical, we call it a classification. So today we will talk about classification with this logistic regression algorithm. So there are two types of classification problem. Sometimes the target variable only has two values, 0, 1, yes or no, dog or not dog. And these are called a binary classification. And sometimes the target variable has a multiple values, multiple unique values. So that's called a multinomial classification. And when we do the classification, there are two approaches to do that. One is called a hard assignment. That means we assign the value, the categorical value, to the target variable, yes or no, 0 or 1. That's called a hard assignment. But sometimes we don't do that. We do the soft assignment, using probability to mean what this target variable is. For example, if it has a target variable with 10 classes from 0 to 9. So what class does this entry is? But if you yeah, you can use the 0 to 9 to represent it, but we don't do that. Sometimes we use instead we use a probability to do that. For example, if for the 0, you assign a probability to each class. And this is the probability for 0, and this is the probability for 1. And each value gets a probability, and then toward the end, you select the class with the highest probability. So here it's this one, be the highest probability. So we, which means that the value should be 7. The class of this entry should be 7. And we use the same method for the logistic regression. Here's some other algorithm, and next week we'll introduce k-linear list neighbors for multinomial classification. So we use the same method, probability, for the logistic regression. We use the probability 0 to mean it's the probability 0 to mean the candidate B, and the probability 1 means it's a candidate A. So example here. You get us a few samples here. This is 0, probability 0, and probability 1. For example, because logistic regression, like regression, what you get is a number. What you get is a number, like linear regression. At the end, you get a formula, and then you get a number. And if this number is, for example, 0.1, 0.1 means that here 0.1 means that it's under 0.5, then it means that the result is 0. Okay, all these are under 0.5, the result is under 0.5. That means that it chooses this this value. And if it's above, the probability is above 0.5, means likely, this is more likely. One is more likely. So the probability of 1 is more likely than 0. So it chooses this group. Okay. Technically, we can still use the linear regression for this model. Okay. You get a linear regression. And then at each x, you get a value like here. Okay, this is below 0.5, so likely it's a 0. Is the candidate A. Okay, and it goes here. Okay, if the x is here, okay, the probability is above 0.5, so likely classified to this group B. However, this line has the two problems. One is that it goes infinite to both sides, and I only need the y value to be bounded between 0 to 1, right? I don't need values probability lower than 0 or higher than 1. That's not possible. So one problem is I need this line to have a boundary. Yeah. And the second problem is if I add more cases, I have more cases, and some cases like here. And I have some cases here. And then this line will not be like this one. The perfect linear regression line could be like this. This will be the one with the smallest distance to all the dots. And then if I do, so this is the number, this probability 0.5 is still here. So if I get the value here with this new line, okay, this is the new line. This one we can erase that. This is the new line. Okay. So now if I get the new value of this x, then this probability is under 0.5. So I could now classify these dots correctly. Because now all these dots, all these one, its probability is below 0.5. It will be classified to these, to A. So they're not using these training samples, these samples correctly. Okay, so this is a problem with this linear regression. Instead of using linear regression, it will be a better fit if it's S-curved, and then all these dots can be classified correctly, and it has a boundary. It has a boundary between 0 and 1. So this is called a Sigmund curve, and also called a logistic curve. And with this logistic curve, the probability of each x, the equation of each x will be, so this means the probability, right? Each y value means the probability. This the probability would be equal to 1 divided by 1 plus e and ax plus by. No, ax plus b. Okay. X plus b. So this x means that this x, and then you got the p-value, and this p-value is between 1 and 0. If this one is close to 0, then this probability is 1. And if it's larger, goes very large, and then it's close to 0. So how do we get this equation? It's a little bit messy. You don't have to remember all this, but how do we get this? So the way this one we calculate is, this is by the odds. We know the concept of odds. Odds means the probability divided by the 1 minus probability. So this is the probability that it's likely B. And then this is the probability it's not likely B, it's A. And then this odds equals did we learn this in statistics? Odds, yeah, odds is a probability divided by the probability it will not happen. Okay, it's a probability it will happen. And this is a probability it will not happen. This is the odds. And this odds can follow. This odds could go from 0 to infinite. It's not like probability. This odds could be 1 divided by close to 0. For example, it could be 0.9. Then this one should be 0.1. if the probability is 1, is a 0.9, then the odds is a no, it's 0.9. Then this is a 0.1. The odds is a 9. And this can go larger, 0.99 and 0.11. So this odds can go infinite, right? It can go infinite. And it could follow a linear regression, but it's actually called a curved regression. It's a follow this equation. So it doesn't go exactly in linear regression, but this odds equals E follow, it has a relationship with the X. It has a curved linear. Is that what you call curved linear, I believe? So this odds is equals this equation, okay? AX plus B, and has this E here. So the odds is equals what we said, odds is equals the P divided by 1 minus P. Take away this, and if you transform this, do a little bit math to transform this, and then it should come to this equation by the end. For example, you flip this and then flip this. Okay, you flip this. And then you get 1 divided by P minus 1. This minus 1 can be moved to the side. Can be moved to the side. And at the end, you got this equation. P equals 1 plus E AX plus B. So toward the end of the logistic regression model, we get like the linear regression we learned, you get an intercept. The intercept is this one. And then you get a coefficient also. The coefficient means, which one means the coefficient here? A, right? A is the coefficient. And then you can write out the same equation like this one to get the probability. Okay. So,
I have some questions.
Yes.
What is the old? Why we need the old?
Oh, we need the odd to calculate the probability. So the the odd follow this line, follow this curve, like the curve linear. So you can get the equation of the odds easily. You can get the equation of the odds with this with the X. So this is the relationship of X and the odds, and then with the odds you get the equation of the P. So it's just a process to calculate the P, and you need to remember this, know this. So when you get to the coefficient and the intercept at the end of the linear the regression model, you will know how to calculate P. Of course, you don't need to calculate it by hand. We use the predict method, predict to get the probability at the end. Yeah.
Is the odds for logical probability?
The odds?
The equation for the odds that you did on the other
Yes.
side?
Yes. So yes, you can use the log to calculate the P also, I believe. you can use the log to calculate this one. But I prefer to understand it in this way. You can do the ln, and then you get to the ln 1 minus p and the minus ln p, and then equals ax plus b, I believe, and then you can also calculate that way. So you understand this equation, and then why we use this sigma curve to fit the samples here. Okay. So when we use logistic regression, there are a couple of assumptions. First, the target variable should be a binary. Okay, it only supports 2 values. And then the second one is the variables should be independent of each other. And if they have a high correlation between the numerical variables, you should remove those variables with high correlation. And this one, the independent variables are linearly related to the log odds. Yes, so the log odds so the log of the odds is linearly related to the x. And also this method requires a large sample size. Okay, that's the explanation of the odds. Okay, next we'll go over a case to understand this better. Using this method as simply like what we did with linear regression. However, the data cleaning method is quite different, because now you have the categorical variable as a target variable instead of the numerical variable. For example, when we try to remove the when we try to select the features in the linear regression, we calculate the correlation coefficient, right? But now you have the target variable is non-numeric, so you cannot use that method anymore, and we need to find another way to remove the features, to reduce the features. Okay. Okay, here I already read in this data set, and the data set is to predict whether this person is likely to have a heart attack or not. And the target variable is 0 and 1. 1 means that he's likely to have a heart attack, and 0 means he's not likely to have a heart attack. And if we load this data, and get a preview of all the variables. You see the variables that could be associated with the heart attack. Age, sex, I believe age is more important than sex. And then these cholesterol level, yes, some of them I'm not quite sure, actually. So let's look at this. The first thing we are going to do is to adjust the missing values. We mentioned there are a couple of ways to adjust the missing value. The first is to remove features that has too many missing values. Which features we couldn't move? So this one, definitely one, these two. Only 3 null values. This one only has the 28 null values. This one, these 3 could be removed. Again, you have to look up the code book and to make sure these are not that important to the target variable. For example, if it's a property, then if it's waterfront, we said it's waterfront. There are only maybe very a few null values, right? Very a few property has the waterfront. It will be yes, but you still want to keep it because you know it's important. So you have to look up the code book whether these 3 could be removed or not. But here I assume they are not that important. I'll remove them. Okay, I just use the code already written instead of typing each one. And after remove these features, we see there's still a couple of variables that has missing data. And there are 2 ways to address this, some variables with missing data. One is to remove the rows, and the second one is to, what is the other way to do the missing data? Yeah, we removed the column, but this column it has quite most of the data. It has most of the data, right? Most rows has this data, so we don't want to remove this whole column. And you know, cholesterol level, it's important. It does affect heart attack, right? So we want to keep it, and but you could remove the remove the rows without this data with the null values. Remove the rows with null values, and also you could what other way? You could replace the null value with a common number. And most people have this cholesterol level. You can replace it with the null value with that common value. So here I dropped the rows with null values. Okay. And now if we check this again, it still have 261 entries. But all the variables has values now. So next one, we want to explore to get an overview of how this data look like in the histogram. So I generated a histogram for each variable, including I generated a histogram for each variable. And if we look at this data, what do we see? The sex, they are more male or female participant than the other gender, right? And also each group is not even. For example, this one, ABS, this value only has a few samples, and this one, most of the, I guess the majority of people are in this group, and only a few. Maybe this one is that you had a previous heart attack, so very few people had this. But however, is one important thing here. We have to watch this is the target variable. This target variable has two groups: heart attack. No, has two groups. One is had a heart attack sample, had a heart attack, and the other group is they had no heart attack. So if that's not even, what will be the problem? For example, if it goes extreme, all the samples here, all the samples we included, they didn't have a heart attack, and we had no sample of people had a heart attack, right? Then you cannot predict this, right? You cannot predict this group. So that's a problem here. Yeah, very important for classification. You need to balance the data for the target variable. Or else it cannot, if this group of sample is very small, you cannot predict this group accurately. So that's another technique we have to deal with when you do classification. Okay. Next. Next up, we are going to look at the numerical values. The numerical values, I plotted a box plot. Plotted box plot for all the numerical values. This code here means it has the 2 rows and 3 columns. Okay, it's the structure of the figure. So so now we have the numeric, the target variable is a categorical 0 and 1, and then this is the numerical value age. And age of people had no heart attack. The age of people had a heart attack. Maybe this is slightly higher. This mean value is slightly higher. Right? People had a heart attack. Mean age, average age is a little bit higher in this group. But is there a real difference between these groups of age? You cannot evaluate. So yeah, for example, this is obvious. There's a significant difference. It's obvious. I like this one. It's not that obvious. These are not obvious. So we have to use the ANOVA to test whether the difference between these groups are significant or not. For example, we still use this one. Okay, we still use this example. This is a box plot. This is also a box plot. these two. This represented people had no heart attack. This is box plot, and that's the age. So these two box plot, even though the mean is quite different, this is much higher. But are there really significant variance between these two groups? I don't think so, because the ranges are pretty the same. However, if there's another plot, smaller, okay. And the mean is also slight different, only slight difference. These two groups has I believe we should have a significant difference. So how ANOVA calculated is it calculates the variance between the groups, okay, I just write it, and the variance within the groups. So the variance with these two examples, the variance between these two groups is same as this one. Variance between these two groups, also as a gap, However, the variance within the group, this one is much smaller, right? This one is much smaller. This one is much bigger, larger. So this one, the difference, this result, this value is much larger, because this variance within each group is much smaller. This number at the bottom is much smaller. So this we call F score. That's the F score. Which group, which plot is larger? This one is larger because the variance within the groups is smaller. The bottom. So we got the F score from the ANOVA test. And this F score means is larger, that means that the difference between the groups is larger. Does that make sense? Kind of just get a general understanding of how to evaluate the box plot. So this group and the difference between the group is significant. This one. And with the ANOVA test, it gives you 2 scores. If it give you 2 scores, so come back to this part where we see they all have a difference between the mean. The means all have a gap. However, I believe which group the difference is more significant. Which variable the difference between the two groups is more significant. Obviously. Between these three. So this is very significant also. The mean variance is bigger, and also so like these three, the mean variance is between the group is quite the same, right? This one, it's quite the same. However, which F score will be larger? Which one? 1, 2, 3. Which one? 3. Yes, because the variance within the group is smaller. So with the ANOVA test, so simply you run this. This new library we use, that's the new method we use called select k-best. And here you can build a model we call this method select k-best. And there are two parameters. One is the function you will use. And for ANOVA test, you use the F classification, F test. Right? And the K means how many features you want to select. Here, I want to generate the F score for all the variables, and I want to select manually. Okay, but if it's a big data set like 25 or 50 variables, then you can set up hey, how many features I want to choose, or 6, 5, or 10. Okay, you can set up this number, and then I just do like like what we did with the linear regression, and you just fit with the x. Here is the numerical variables, and whether they are significant between the two groups, and that's a y. Y is the target variable. Okay. Target variable is the df and target. And the the x variable is the df with all the numerical variables. With all the numerical variables. I'll just copy this list. Okay. So it's really quite the same with the one we use, model ANOVA. So we build this model, and then what we will get is this first, and then what we will get is the scores. I believe it's this one, scores. And this one we'll get to use the F score for all the variables. And also you can print the p-value for each variable. Just copy the code of p-values. Do these separate. Well, let's look at the F scores and the p-values. We said F scores, the larger the difference between these groups is more significant. So here we get the F score, this one. Look, this is the last one. The last one is the highest. And these three, we said that this one might be the difference between these two groups is more significant than these two, right? And this F score is also higher, obviously. So it verifies that agree with our observation. And there's also value. Usually we don't use the F score, but instead we use this p-value. Okay, if the p-value is smaller than 0, 0.05. That means that the difference between the group is significant. We reject the null values, the null hypothesis that there's no difference. So if the p-value is smaller than this one, the difference is significant. Like this one is 0. It's really not the difference, right? And then this one is also significant. These two are still significant, but it's closer to this number now. So the smaller the p-value is, and the more significant the difference between the groups. Just need to remember how to understand this table. Okay. So next, we come to the category variables, category features. So the ANOVA test is for numerical value vs numerical value vs the target variable is the categorical. Numerical value vs the categorical value. However, some of the variables in this is the sex, gender, and some of the other ones, they are categorical variable. Vs the target variable is also categorical. So how do we tell whether they are different? Is there a significant difference between these two groups? If we observe this plot, by just we are watching this plot, for example, this gender, does this affect does this affect the target variable? Or means this one, okay, this is the male. Males are more likely to, for example, this is having heart attack. More males have a heart attack than the females. Females had a heart attack, only a small portion here compared to it's really high. This is the group of females, right? Females. And this is the group of males. Males that have more people had a heart attack, and the females that had very few people had a heart attack. So we would assume that there's a significant difference. It's affected by gender. And for example, this one, I'm not sure. In each of these three groups, this proportion, this ratio is almost the same. Maybe 2 and 1, and 2 and 1. So not sure if this variable affect heart attack or not, the probability of a heart attack or not. Does that make sense? So giving another example, this one, do you think that each group has a different probability of getting a heart attack? Which group has more probability to get a heart attack? These two groups.
The one on the right.
Right one. Yeah. More people had a heart attack in this right group. So this variable, I would assume it's significant. Significant effect on probability. Okay. So yeah, that's how we read this grouped bar plot. And also we can use another method to get the scores and to to get the scores and to evaluate the hard numbers. To select the features with the hard numbers. That's called a chi-square. Chi-square. So we'll come back and to explain chi-square next lesson. I want to save 20 minutes for you all to review the assignments from last week and to answer any question. Okay. Oh, yeah, so the assignments for this week is open. You can start and follow the instruction. But we need to understand these math concepts, and so we can do the data cleaning better. And overall, when you build a model, what we are doing is to select to find the features that are relevant to the target variable. Right. So these concepts are really important. Start. No. What we are doing is the not linear, not polynomial regression. So this is the one is for the this one is for it's the x1, x2. It's because xb, xa, xb. So that's two variables. But not one variable, one is x, and then you get the second one with x squared. So I want to write this x squared. So we can use x1, x2 on other way to explain that. You can use the a or b. That's also fine. But what this represent? What is this represent? What does this represent? X1 represents. That's right. So x1 represents. To insurance.